Okay, so now that we know what pigeonhole principle is, let's try and prove this property here. So I want to prove that this language L cannot be recognized by any DFA. Languages that can be recognized by DFAs, we call them regular languages. So a regular language is one that is any language that can be recognized by a DFA. Recognized by a DFA. Okay, so we want to basically prove that this language here, L, is non-regular. Okay, how are we going to do that? How do we prove something doesn't have a property? We usually assume it is and derive a contradiction. So we're going to proceed by contradiction. So proof by contradiction. Okay, how do we do a proof by contradiction? We assume the opposite. So I'm going to assume that L is regular. If L is regular, what does that tell me? Well, if it's regular, then there is some DFA that recognizes it. So there is some DFA. I'll call it A, such that the language that A recognizes is equal to this set here, curly L. All right. Now, what we want to do is I want to sort of take a string from this set and use pigeonhole principle to like pump one part of it up and try and prove that the DFA accepts strings that aren't in the language. And what's going to help us doing that is the append theorem, right? So what was the append theorem again? The append theorem tells me from some state S, if I read alpha beta, I see where alpha takes me and I see where beta takes me. So if we note, so the front of the string is 0 to the end. So we're going to note that the set, I'll call it E, comprised of epsilon, 0, double 0, triple 0, da 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 da, is an infinite set, right? It's got infinitely many elements. Clearly, right? You ain't got an arbitrary number of zeros in a row. It can be as long as you please. So, what does that tell me? Well, from pigeonhole principle, that tells me that from the starting state, there's going to have to be two strings in this set that go to different places. So, there exists alpha, beta in E, with alpha not equal to beta, such that from the starting state, if I read alpha, I get to the same place from reading beta. Okay? Now, since alpha and beta are in this set, alpha and beta are going to be some string of zeros, but not the same strings of zeros, right? So that basically means there's going to exist some index I, exist some index j, with I not equal to j, such that if I read I many zeros, that's going to get me in the same state from reading j many zeros. Alright? This here is just an equivalent thing as above. Okay? How can we use that property? Well, 0 to the n, 1 to the n is always accepted for any n, right? So I'm going to choose n is equal to I and try and get a contradiction. So if n is equal to I, clearly 0 to the I, 1 to the I is in the language L. If it's in the language, that means the DFA must accept it, right? So A, the DFA A, accepts the string 0 to the I, 1 to the I. Okay? What does it mean to accept a string? It means that from the starting state, you get to a final state. So from the starting state S0, if I read 0 to the I, 1 to the I, I'm going to end up in some final state F. Okay? Now I can use the append theorem to break this up. So whatever this state is, it's a final state, and it's going to be the same as this state, right? The state obtained from the initial state, reading I many zeros, and then from that new state, reading I many ones. Now, what's this state here in the middle? Well, I know from applying pigeonhole principle, reading I many zeros from the initial state is the same as reading j many zeros. So I can swap these two terms out. Alright, so from the initial state, reading j many zeros followed by I many ones. And this state here is going to be the same as this state here. I can now do append theorem backwards and put it all back together again. 0 to the j, 1 to the I. Now since each of these terms are equal, that means whatever this state is the same as this state here. Since this state here is a final state, this state here must also be a final state. So that means it's a member of the set of all final states. Therefore, 0 to the j, 1 to the I is accepted by A. Now, since A recognizes the language curly L, that means 0 to the j, 1 to the I is a member of L. Okay? What strings were members of L? Strings with the same number of zeros as the same number of ones. So for this string to be in this language, it must be the case that j is equal to I. But I've got over here that I is not equal to j, right? These two facts contradict each other, so we denote a contradiction by a little lightning bolt. So because I obtained a contradiction, that means I must have made a bogus assumption, right? And clearly all the steps along the way in my proof was legit. So what went wrong? There must have been a bogus assumption somewhere, and it looks like the only assumption I'm making is this assumption here, right? Assuming that L is regular, and then I got a contradiction. Therefore, it must be the case that L is non-regular. So therefore, any DFA you choose will not recognize this language. This language is totally unrecognizable by DFAs. And that completes the proof. Okay? If you've got a bit of a maths background, you could see another way to prove this that is non-constructive. That is, it doesn't give you an example. How many possible DFAs are there? How many possible DFAs could create? Infinitely many, surely, right? It happens to be the case that we can enumerate them. What does that mean? It means I can sort of write them all down in an infinite list. How can I do that? Well, I could write out all possible one-state DFAs. How many one-state DFAs are there? Well, I guess all the transitions have to go back. So I guess there's this one. And the same DFA with S not being accepting. I guess those are the only two possible DFAs with one state. And then how many DFAs are there with two states? Well, if I've got two states, S0 and S1, where does 0 go for S0? I guess I've got two choices, either back to itself or to S1. I got two choices for the 1 transition, back to itself or to S1. I got two choices for S1 again, so it looks like I'm going to have 2 times 2 times 2 times 2 many choices, gives me 16 choices. And then I got two choices for this being final or non-final, 2 choices of this being final or non-final, so it looks like there's going to be 64 possible 2-state DFAs, right? And how many possible 3-state DFAs are there? Well, a large number, but certainly finitely many. How many 4-state DFAs? Again, finitely many. So it looks like I could write out every possible DFA in a list. I can enumerate them. So if you've done 1115, you might call this countably many, right? Because we can list them and we can list them all. There's the same number of DFAs as there are natural numbers. How many languages are there? Well, the set of all languages, that's going to be equal to the power set of the set of all binary strings, right? Because every language is just a collection of strings, which is going to be a subset of the set of all binary strings. So that means the set of all languages is the same as the power set as the set of all strings. Well, how many possible strings are there? Countably many. So how many sets of strings are there? Uncountably many. That means the number of sets of strings, that is the number of languages, is a bigger infinity than the number of DFAs, loosely speaking. That means there must exist languages that can't be recognized by DFAs, right? Because if you try to pair up all the languages with DFAs, you're always going to get leftovers, right? Because there's more languages. Even though they're both infinitely large sets, this one's bigger. If you don't understand that, that's totally fine. I just wanted to sort of add this in as a side note. The important thing is you understand this proof here. So this is like a constructive way to show because that there are languages that DFAs can't recognize, because it gives you an explicit example. This one here can't be recognized. This proof also works, but doesn't actually point to an example. It just says that they're out there somewhere, right? So this proof here we would consider to be a better proof.